Okay, woohoo, here we are. Amino acids. So this, I don't even know what to call this. Video. Okay, so this video is all about memorizing the amino acid structures, their names, their 3-letter codes, and their 1-letter codes. You should be able to draw structures at any pH between 0 and 14. That's where the pKa video is going to come in. It's going to help you be able to determine the charge of the amino acid functional groups at any pH between those, between 0 and 14. You're also going to have to be able to classify each of the amino acids as nonpolar, polar neutral, polar positive, or polar negative. So I'm going to go through the basics of the amino acids, and then I'm going to draw all 20 of them so you can have seen them at least once. All right, here we go. Okay, so we got to let's talk about the basics. Okay, so there's 20 different, AA is for amino acids. There's 20 different amino acids that you need to know by heart. Okay, and they all have a basic architecture or a basic structure. So let's go through that first. So all the amino acids have an NCC. We call this the backbone. It contains an NH3 plus. This is the amino functional group. Hopefully you remember that. It contains a carboxylic acid over here. I'm going to call it the C acid. And then in the middle, there's a carbon attached to a hydrogen. We call this the alpha carbon. Okay, and then what is coming off of the alpha carbon are all of the different side chains. So R differentiates into the 20 different amino acids. Now, I wonder why they call them amino acids. Oh, I wonder if it's because there's an amino and an acid part of each one of them. That's why they're called amino acids. Amino acid. Meow, meow, meow. Food for thought. You'll also need to have the pKa's memorized for functional groups that are relevant to the amino acids. So I'm going to go ahead and add those in to this video so that you have them. The backbone amino group has a pKa that is 10. And the backbone carboxylic acid has a pKa equal to 2. Now, if you were to look these up in a textbook or online, you'd see that they're not exactly round numbers. They have decimals and things like that, but you don't need to memorize those decimals. You need to just memorize these whole numbers. The other thing that you need to notice is that these amino acids, they're all chiral. They're all chiral. They have a stereocenter right at the alpha carbon. All of them except for one, which is glycine, and you'll see. What you do not have to do, you do not have to draw these with the right stereochemistry. Don't worry about that. The other thing that might come up on your MCATs, PCATs, whatever kinds of exams you might take, is the fact that these amino acids are all L amino acids, not D amino acids. So L and D, these are prefixes that are similar to the R and S system for assigning priorities for chiral centers. Not exactly the same, but we use them in biochemistry. The way that I remember the biologically relevant amino acids are all L is because you love amino acids, and L, love starts with L. So all of the amino acids that are biologically relevant are of the L stereocenter, and let's just leave it at that. Okay, so let's go ahead and get started. We're going to go through the non-polar ones and then polar neutral, polar positive, polar negative. I thought about making separate videos for each one of these, but I think maybe instead I'll just have one video for all the amino acids, and you can pause it and rewind it, and that way you don't have to open 5 different videos. So it's probably going to be a little bit longer, but again, I had intended to chunk them down into small videos, but that just seems like too much. Okay, so let's start with the non-polar amino acids. And these are going to be the non-polar amino acids that are also considered aliphatic. Aliphatic means no double bonds. And again, I'm going to draw all of these at pH 7. When you watch the pKa video and the PI video, you'll learn how to draw them at any of the pHs that are between 0 and 14, but I'm going to draw them specifically at pH 7. Okay, so as always, you're going to want to start with your NCC backbone. So I'm just going to draw a couple of these already. And of course, the backbone has the NH3+, the alpha carbon, the carboxylic acid. Okay, and it's what comes off of that alpha carbon that differentiates all of them. So the simplest one is just to add a hydrogen. This makes it glycine. So one-letter code is G, and its three-letter code is GLY. And the three-letter codes, only the first letter is capitalized. Food for thought. Glycine is obviously the only amino acid that is not chiral, because coming off of that alpha carbon are the same two groups, two hydrogens. Okay, moving on. If we change that hydrogen into a methyl group, we get alanine. ALA and A. This should be a capital A. Okay. Next. Just so you know, there are 5 of these nonpolar aliphatics, so space this out appropriately for yourselves. Okay, so 2 more. NCC, NCC, NH3+, NH3+, carboxylic acid, C double bonded O, CO, alpha carbon, alpha carbon. Okay, so we're just going to keep building off of this alanine. It's going to get bigger and bigger every time. So we'll have a carbon. The next one is valine. And coming off of this are 2 more carbons. And this one looks like a V. So this is valine, VAL, and a V. All right. The next one is a derivation of valine, but you get to add 1 extra carbon. So we'll go a CH2 and then to the V. There's 3. Okay, there's a hydrogen there. I'm going to scoot this over. This is leucine, LEU and L. I just had a thought. Oh, right, you don't have to, so I'm drawing these in what's called condensed formula. You can draw them in condensed formula, you can draw them in skeletal formula, you can draw them in Lewis structure. Skeletal will probably save you the most time, which can be nice. Whoops, hey man. Okay. And lastly, so I said we had 5 of these, again, NCC, H3+, O, O-, H. The last one is an isomer of leucine, which means it has to have the same number of atoms. They're just rearranged differently. So we'll have a carbon to the methyl, and then the chain continues on down. An H right here. This is isoleucine, which means it's an isomer of leucine, so they have to have the same number of carbons coming off the side chain. They're both 4, so that makes them derivations of a butyl group. It's ILE is the 3-letter code, and just I. There you go. Those are the nonpolar aliphatics. These ones are going to be the nonpolar aromatics. And there are 3 of them. Okay, so I'm going to put NCC, NCC, NH3+, carboxylic acid. Again, these are all drawn at pH 7. H. Okay. Coming down, CH2. Actually going to add a CH2 to both of these. The simplest nonpolar aromatic adds a phenyl group to what would have been the methyl group. So it's kind of a combination between a phenyl and the alanine. So it's called oops, spelled that wrong. Phenylalanine. Alanine. PHE and F is its one-letter code. The next one is tyrosine, which is a phenol instead of a phenyl. Tyrosine, TYR, and Y is its one-letter code. Tyrosine has a relevant pKa. That's this group right here has a pKa that is 10. So that is one of the ones you're going to need to memorize and associate with tyrosine. Okay, and then the third nonpolar aromatic is probably one of the hardest amino acids to draw. So start with your CH2, and then this is a bicyclic ring. One of them is 5-membered with a nitrogen at the center of it, connected to a 6-membered ring. Double bond here, here, and here. Double bond here, and the double bond here, none of the double bonds ever touch that nitrogen, so that's one of the ways that I remember where to put the double bonds, is that the nitrogen is usually opposite of, the nitrogen is usually opposite of this carbon right there, and it never gets a double bond. Okay, this is tryptophan, whoops, wow, yikes, let's go back. Tryptophan, TRP, W. If you look at it, it almost looks like there's a W in the structure. So that's how I remember that that has a W. Okay, so those are the nonpolar aromatics. We have 2 more nonpolars to do, and we'll do this on a new. So these are our last 2 nonpolars. Again, like I said, there's 2 of them. NCC, NCC, NH3 plus, H, double bond O, O minus. The first one is methionine. This is one of 2 amino acids that have a sulfur in them. Okay, methionine, MET, comma, M. All right, this other nonpolar is the only one that you don't want to do the NH3 starting with, because the nitrogen here connects up to the alpha carbon. So there's a 5-membered ring, and you get NH2 plus, because there's an extra bond coming, the extra bond on that nitrogen is coming down and connecting back up to the alpha carbon. This carboxylic acid on the backbone is still the same. This is proline, pro, and P. All right, so those are the nonpolars, the nonpolar aliphatics, the nonpolar aromatics, and then the 2 that are just a little bit goofy for the nonpolars. Next, we're going to move on to the polar neutrals. Okay, so these are polar neutral amino acids, and again, everything here is drawn at pH 7. If it's polar neutral, that means at pH 7, the side chain should not have a charge. There are 5 of these, so space it out appropriately on your note if you're taking notes. NCC, NCC, NH3 plus, carboxylic acid, alpha carbon, NH3 plus, alpha carbon, carboxylic acid. Do you see a pattern yet? I hope that you do. Okay, and again, I'm going to put a CH2 here. Food for thought, if this is the alpha carbon, this one is beta, and they go on down the line in the Greek alphabet as you go down in the side chain. So alpha, beta, gamma, delta, epsilon, so on and so forth. Okay, food for thought. So coming off of the beta carbon, if we add an OH, that makes this serine. And that is SER, comma, S as the 3-letter and the 1-letter codes. If I switch the OH out with a sulfohydryl, I get an SH, and that is cysteine. CYS and a C. And this right here has a pKa of 8. Now you're going to notice that I didn't put a pKa on that OH. While it has a pKa, meaning we could lose this hydrogen, the pKa is so high that it's actually not biologically relevant. So, food for thought. Did it again. Okay, scooch it up. 2 more. Well, 3 more, but I'm going to 2 at a time. NH3 plus H, carboxylic acid. I think I'm getting better at drawing. I'm not sure. Okay, so the next one is going to be another one that has an OH coming off of it, but it's just a little bit different. So we're going to carbon to a methyl group to an OH. So this one also has kind of a V shape to it, kind of like Valine. This is threonine, 309 THR, comma T, threonine. Again, no pKa here, so this would not be charged at any of the pHs between 0 and 14, so leave this side chain as neutral. The reason cysteine is here in the polar neutrals is because at pH 7 it has no charge. If we go above a pH of 8, then it gets charged. So again, that's why it's in the polar neutrals, because at pH 7 it has no charge. Okay, and then the last two here are very similar to each other. So CH2 ending in an amide or an amido group. NH2. This is called asparagine. 3-letter code is A, S, N, and the 1-letter code is N. One of the hardest ones to memorize because I don't know, the word asparagine is just kind of odd. Okay, and then the very last one, NCC, H3, alpha carbon, carboxylic acid. Oh man, come on. Okay, it's just like asparagine, except for there are 2 of these methylene groups. So a methylene is kind of like a methyl, but it's missing one of the hydrogens. So 2 methylene groups are 2 CH2s and then the amide. Again, no pKa's for either. Oh, sorry, this is glutamine. Glutamine. GLN is the 3-letter code, and the 1-letter code is Q. Why Q? I have absolutely no idea. I find it to be very bizarre. So some common misconceptions that students tend to hold is they think that threonine, serine, asparagine, and glutamine can all be charged, can all become ions at pH 7, and that is just not true. These are all neutral at pH 7. So I didn't give you pKa's for asparagine, glutamine, serine, or threonine because I don't want you to take hydrogens off of these side chains. Okay, you can take one off of cysteine under the appropriate circumstances. All right, food for thought. We've got 1, 2, 3, 4, 5 more. 5 more. Yeah. Okay, almost there. So here we go. I think I've been using yellow. These are polar, and they're positively charged. The book and some other resources may also refer to these as being basic. I'd prefer that you don't use that terminology. It tends to just confuse students. Instead, I would just like you to refer to them as the polar positively charged amino acids. And there are 3 of these, so space that out for yourselves. NCC, and these are pretty big amino acids structure-wise, so give yourself some space. O-, alpha carbon, Alpha carbon. Okay, so the first one has 4 methylene groups. 1, 2, 3, 4, and then an NH3 plus. At the bottom, this is lysine, Lys, comma, K. And this group right here has a pKa of 10. This one over here is also another very tricky one to draw. There are 3 methylene groups. Sorry about that. CH2, 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 followed by the guanidinium functional group. So that's NH, carbon, nitrogen, nitrogen. One of these gets a double bond. Oops, I keep doing that. NH2, positive. The other one does not. And this is Arginine, Arginine, ARG, and R. The guanidinium functional group has a pKa of 12. And only one of the nitrogens at the bottom will be charged. It always has just a +1 charge if it is fully protonated. Let's see. Tricks of the trade here. If you start at the alpha carbon, you can actually spell lysine, sorry about that, E coming down. So that's how you know how many, total atoms. Doesn't really tell you what those atoms are. If you do the same thing with arginine, you can also spell arginine here. A-R-G-I. Look, the N and the N match up. I-N-I-N and E. So 2 of the N's in arginine actually tell you where 2 of the N's will go. I don't know if that helps you or not, but that's one of the ways I learned how to memorize it. You'll come up with all sorts of interesting things to tell yourself. College kids are good at that. Okay, and the last one is CH2, followed by the imidazole functional group. So I don't know if you remember that, but that's the nitrogen that is every other one. First nitrogen gets the hydrogen, then the double bond, then the double bond here. I'm going to leave this uncharged. Sorry, this is histidine. His and H. I'm going to leave it uncharged because it's the pKa of the imidazole is 6. Okay, so at pH 7, this is actually unprotonated. It can be protonated if we go above 7, but they always put histidine with the polar positives. I know technically it's polar neutral at pH 7. We'll get into a little bit more about histidine, but I would argue that this is probably the most important amino acid because it has a pKa that is so near to 7. To the pH of 7, it makes it, what do I want to say? It makes it versatile as far as reactivity. So please learn how to draw histidine. I know it's a tricky one. But at pH 7, histidine is neutrally charged, and if you watch the pKa video, you'll learn why. All right, we have 2 left. Those are the polar negatives. Here we go. Back to yellow. Polar negatives. I think these are pretty easy to draw. They look very similar. Again, the same with the polar positives, that sometimes people call them basic. They would call these ones acidic. Again, I prefer that you don't say that about them because I think it makes it too confusing. And there are only 2 of them. So we'll do our NCC, H3 plus, alpha carbon gets the hydrogen, minus, NH3 plus, alpha carbon, carboxylic acid. Okay, so these 2 are derivations of asparagine and glutamine. So we get I'll put one methylene group here. I'm gonna put 2 of them here. And in asparagine, we had an amide group here. For this one, we have a carboxylic acid. So we just replace the NH2 with an O-, and we get aspartic acid. Remember, the ic acid also could be an 8. So sometimes people also call this aspartate. 3-letter code ASP, 1-letter code D, no idea why. Over here for the second one, instead of glutamine being the amide at the end, it's again a carboxylic acid, and we call this glutamic acid. Glutamic acid, also known as glutamate. Whoops. Spelled that wrong. Glutamate. GLU is its 3-letter code, and E. It's 1-letter code. The way I remember that is that glutamate has more methylene groups than aspartate, so it is the next letter in the alphabet. So we go from D to E. Again, aspartate and glutamate are derivations of asparagine and glutamine. Hopefully you'll be able to draw some correlation patterns with those. And last but not least, the functional groups here. I'm just going to circle them both because I have the same pKa here is 4. Okay, so those are all 20 amino acids drawn at pH 7. Again, you do not need to draw stereochemistry. I did not do that. You can draw them in condensed, you can draw them in skeletal, but you do need to know all of their structures. It is so critical to understanding the language of biochemistry. They're 1-letter codes and they're 3-letter codes. And thanks for watching, and I'll see you in class. Bye.